Hi, I hope everyone had a good spring break. I guess everyone is aware at this point that we're going to be doing things a little bit differently for the rest of the semester, switching to an online learning mode. I'm new to this. I'm sure many of you are as well. So, appreciate any feedback on what we can do to make things better, perhaps for both of us. Right now, I plan on at least initially doing lectures asynchronously. That means, I'll record them. You can watch them at any time. I'll still be relying heavily on my web page um, to have links to the video, also have the homework assignment. I am starting to incorporate Blackboard into the course a little bit. In particular, I would appreciate it if you have questions or want to discuss anything that you post it to on Blackboard in the threaded discussion. I am still looking for a way to collect homework, so I may actually have you scan the pages in using your phone and upload the homework again to Blackboard, and then I'll grade it there. We have a test coming up in a couple weeks. Actually, I think we're finishing up chapter 8 today, and we're supposed to have our next exam after chapter 10. I'm looking at options there for online testing. So you guys are going to have to get a comfortable learning environment where you have good Wi-Fi. But right now I'm investigating looking at giving exams via Blackboard as well. Okay, so let's go on to today's lecture actually. And last time we had started discussing channel allocation in chapter 8. We finished most of that, so it was actually different methods for allocating a fixed number of channels to users, and most of it was just a discussion of different methods that are used. We want to actually get into some modeling, mathematical modeling of channel allocation today so that we can work through some analytical problems. I'll work through an example problem also today. So in this system modeling problem, our assumptions are that the mobile stations are uniformly distributed throughout the cell, and each is moving at a random speed in a random direction. There are two arrival methods. One is users who are in the cell who start to make a call. That's called originating a call. Those arrival rates are given by lambda 0 here. So that would be like 3 calls per hour. The other way in which we can allocate channels is due to handoffs. So this would be to users who are currently on a call who move from an adjacent cell into our cell, and we have to allocate them a channel so that they can continue the call. And then the call service rate is denoted by this mu parameter. Okay, and so here's a graphical model of what's going on there. We've got capital S channels available in our cell. Any of the S channels might be allocated to either an originating call or a handoff call. Okay. And here's the notation. This is similar to the notation we used in chapter 2 where we talked about queuing theory. So you may want to go back and review that information briefly. But P of I represents the number of I channels that are busy. So if I is 0, that means all S channels are available. For P of S would be the probability that all S channels are busy, and so that no channels are available, and so that would consequently be the probability that any originating calls or any handoff calls would be blocked. And then B0 is the blocking probability of originating calls. That'll be one of the parameters we're interested in, as well as BH, the blocking probability of a handoff call. You'll see in our first model that B0 and BH are equal, that if all of our channels are in use, any originating calls or any handoff calls will be blocked. Okay, so here's a state transition diagram. In steady state, we assume that the transition rates incoming and outcoming are equal, and so that leads to this equation: I mu P of I is equal to lambda 0 plus lambda H times P of I minus 1. So we can solve this equation for P of I quite simply, just divide by I mu, and we have an expression for P of I in terms of P of I minus 1. So by induction, we can extend this down to an expression where we have P of I in terms of P of 0. So this is the given expression. We need to find P0 so that P of 0 so that we can determine the P of I. The other equation that we have is that the sum of the P of I's has to equal 1. So we have to be in some state, either all lines available when I is equal to 0, or no lines available when S is equal to, when I is equal to S. And so we have to be in one of those states, so P of I has to equal 1. So if we sum up the P of I's here from 0 to S and set that equal to 1, we can solve for P0, and we get this expression for the probability that no lines or no channels are in use, or all channels are available. So we can take this expression and plug it in into this formula here and come up with the probability that I channels are in use. Okay, finally, the blocking probability for either originating calls or for handoffs, they're equal in this case, is equal to the probability that all S channels are in use. And so that's given by again, this messy expression. That's P of I with I equal to S times P of 0, and P of 0 is 1 over this term in the denominator here. So this is the blocking probability. You can simplify the formula a little bit by letting lambda 0 plus lambda H over mu be equal to A. A is what we called the offered load back in, I think it was chapter 5. And then so you could rewrite this formula, or the P of I formula, in terms of A much more simply as A to the S over S factorial divided by the sum of A to the I divided by I factorial. In that form, you can recognize it as the Erlang-B formula, which we talked about in chapter 5, and is also tabulated in the appendix at the end of the textbook. Okay. A slightly more complicated model gives priority to handoff traffic. And why would we want to do that? It's a lot more annoying to have a call dropped as we go from one cell to another than it is for a user who's trying to make a call just to get a busy signal. So we want to put a higher priority on handing off calls than originating calls. One approach to doing that is actually to reserve a certain number of our channels exclusively for handoffs. So that's the next model we're going to look at, where we reserve SR of our S channels for handoff, and those SR channels will not be used then for originating calls. So graphically it looks like this. Lambda H can actually feed into any of our S channels. Originating calls can just use SC out of our S channels. And then so SR is equal to S minus SC, and that those SR channels will be exclusively for handoffs. Not only for handoffs, other channels can also be used for handoffs, but those SR channels will not be used by originating calls. Okay. So the transition diagram changes a little bit. We get different equations depending on whether it's one of our first SC channels or one of our channels reserved for handoffs only. Again, the sum of these probabilities has to equal to 1, so we can use this to come up with an expression for PI in terms of P0. Again, two different expressions depending on whether I is between 0 and SC or between SC and S. We have the requirement that the sum of all these probabilities is equal to 1. So we can use that to actually solve for P of 0 and get this rather complicated looking expression down here at the bottom of the slide. And then finally, the blocking probability of an originating call is going to be equal to the probability that SC channels are busy, or SC+1, which means that one channel is being used by a handoff, or SC+2, which would be two channels are being used by handoff, but all SC channels, which are only used for originating calls, are busy. So B0 would be the sum of the probabilities from SC to S. On the other hand, we're only going to block a handoff if all channels are busy, all S channels are busy. So looking back on the previous slide, substituting in here with I equal to S, that's going to give us the probability of blocking a handoff call. Okay, so what I want to take a look at now is actually a problem from the textbook. I meant to pull that up here, but I didn't get that web page open, or forgot to open that up before the video. So let me actually just write down the problem. So this is based on, here we go. This is problem 8.18, but I've modified it a little bit. So I'm going to work the problem assuming that all S channels are available for both originating calls and handoffs. So there are no reserved channels. Okay. Again, S equal 4 would be a small number of total channels available, but this is a homework problem, and you'll see that at least for working this by hand, I'm going to have to keep the number of channels actually at a small number. For larger values of S, you really want to use a computer. Octave would be ideal to solve these types of problems. The other change I'm going to make is we're given here the arrival rates of both originating calls and handoffs is 0.001, and then mu, I'm going to use a value of 0.0012. I think in the textbook, in the problem, it says 0.0003. I'll use a slightly larger value for reasons I'll explain later. And then what we want to solve for in this problem, or the probability of blocking an originating call, the probability of blocking a handoff. And again, in my modified problem with no channels reserved for handoffs, these two are equal. And then we're also asked to find each of the probabilities of 0 through 4 channels being in use. And then finally, we're asked to find the expected number of channels that are in use. Okay, so to simplify the notation a little bit, let me define this A value. Again, it's what's essentially the offered load. It's lambda 0 plus lambda h over mu. This would be the total offered load to the system, and that's going to be 0.002, twice the 0.001 divided by 0.0012. And that turns out to be 1.667. There isn't a requirement that A needs to be less than the number of channels in order for the system to reach steady state. With the value of mu given in the homework problem of 0.0003, that condition is not met. So you can still go through the formulas and crank out numbers, but they're essentially meaningless. So that's why I changed the value of mu here. Okay, from equation 8.7, we have that the blocking probability of originating calls is A of S over S factorial over the sum from I equals 0 to S of A to the I over I factorial. So I need to compute this thing. It's actually not too hard, again, when the number of channels is small. So let me actually just make a little table of I, A to the I over I factorial. So for I equal to 0, this is equal to 1. For I equal to 1, this is 1.667. So 1.667 to the first power divided by 1 factorial For 2, it's 1.667 squared divided by 2 factorial, which is 2. So this turns out to be 1.389. For 3, I get 0.772. For 4, it becomes 0.321. Okay, and then now I can get the sum of the AI over I factorial by just summing these 5 values. That turns out to be 5.149. Okay. Let me make a table of P0. I'm sorry, PI values. P0, looking back on the slides, is actually 1 over this value. So that's 1 over the sum of the I factorial, or in this case 1 over 5.149. Sorry, my handwriting's so sloppy here. I'm still getting used to actually doing this on a tablet instead of with a marker. So P of 0 turns out to be 0.194. And I'm afraid my battery on my pen is dying. Okay, it looks like maybe it's back. Hopefully it'll last for the rest of the lecture. 0.1941. And then the P of I were given by, where do I have that formula written down? They were the, let's see if I can recall it from memory, A to the I over I factorial times P0, essentially, or divided by that sum term. And so using that, I've got the AI over I factorial, so just multiplying each of these times P of I get 0.3238 and 0.2698, 0.1499. Just like the way I wrote that number, and 0.0623. Actually, if you sum all these up, you should see that they actually sum to 1. In this case, I think they sum to like 0.998, so just due to some rounding error. So these are the individual PIs, which we were also asked to find. So BH is equal to B0, again, in my modified problem. And then finally, the expected value, well, of any random variable, a discrete random variable, is just going to be the discrete random variable value times the probability. So here, this can take on values between 0 and 4. And then so we evaluate the sum, 0 times 0.1941 plus 1 times 0.3238, so on and so forth. And we get for this expected value 1.562. Okay, for homework, I'm going to assign the same problem, 0.8.18, but unmodified, as it's written in the textbook, with S equal to 4 again, but with one channel actually reserved for handoffs. Use this value of mu, though, not the value that's given in the book. And then the other problem I'm going to assign is problem 8.19, which actually 10 channels, one still reserved for handoffs. Use these same values for lambda 0 and mu. For the 10 channel case, I would highly recommend actually using Octave to do the computation. It's really not necessary, I guess. In that case, 10's a small enough number you could work out the table by hand. But again, I would recommend using a computer program to do that. So I think that's it for this lecture. Relatively, do I have anything to tell me how long I've been going? Looks like about 20 minutes on this lecture. If you play this thing back double speed, you're done in with the lecture in only 10 minutes, giving you quite a bit of time to work on the homework actually. So see you next time. I'm still working on, again, some online software for synchronous discussions, and I'll be sending out additional information via email, so make sure that you check your email frequently. Hope you're not going stir crazy from being inside. I know I am a little bit, but we'll get through this together. So talk to you soon.